Today we will talk about the intermediate value theorem. This is a theorem that is about continuous functions and often shows up in a course on calculus. And it says the following. If a and b are real numbers with a less than b, and f is a continuous real valued function on the closed interval a to b, then for any real number, let's call it gamma, between f of a and f of b, there exists at least one point C in the interval from A to B, in the open interval from A to B, such that f of c equals gamma. Now, if you don't like this is how it's presented in the book that I'm using, but if you don't like the gamma, you can just replace it by something else. Alright, we won't prove this in this video. It requires some real analysis to prove this. Okay, let's draw a picture just to illustrate what's going on. So let's say A is here and B is here. And f of A is, so f is some function, so let's say f of A is here. And let's just say that f of B is there. So when you plug in A, you get f of A. When you plug in B, you get f of B. And let's say f of B is here. Okay. So it says for any real number gammas between f of A and f of B. So gamma is some number in between. Let's say it's here. Okay, so here's y equals gamma. Then there must be at least one point C such that f of c equals gamma. In other words, there's some C in between A and B such that when you plug it in, you get gamma. So let's just look at an example. So let's just draw a possibility for f. So let's say f is, so I have to go through this point and that point, right? So let's say it's, let's say that's f. Well, so this is the graph of y equals f of x. Well, you can see that in fact this graph, I should make him look more like the graph of a function, because right now it doesn't look like the graph of a function. Oops. Okay. There we go. That's y equals f of x. In this picture, there's actually multiple possibilities for C. So here's one instance of C. Right there. The point is that the graph of the function y equals f of x has to intersect the line y equals gamma at some point. That's what the intermediate value theorem says. Okay, and intuitively it makes sense that it would be true. I mean, it'd be weird if it wasn't true, because if you have a continuous function, one way of thinking about continuity, the intuition, is that you can draw the graph without having to lift your pencil. Okay, that's not precise in any way, but that's sort of a mental picture of continuous functions. And if you have this point f of a and this point f of b, right, so here's f of a, here's f of b, it's virtually, I mean, you can see that if you have a continuous function, it's not going to be possible to get from here to here, right, without crossing this line. That's what the, and you know, so that's why the intermediate value theorem is plausible. The proof is a bit, it's not that complicated, but it requires some more familiarity with advanced properties of the real number system. So it's usually explained in the course in real analysis. All right, well, let's just look at some applications of this theorem. So one main application is for showing that polynomials, or showing that certain functions have roots. So for instance, okay, give me one moment. Well, let's see, I had an example in mind, but I'll just make it up. I don't know what happened to it, but let's just say that you had x cubed plus x minus 1. So the claim is that this has a root in the interval from 0 to 1. Alright, why is this true? How do we know this is true? Well, we can apply the intermediate value theorem using a equals 0 and b equals 1. And of course, this is going to be your f of x, right? Because the intermediate value theorem says, okay, so a is less than b, f is a continuous function on the interval from a to b. Okay, so why is f continuous? Well, because it's a polynomial, right? And polynomials are continuous. Then for any real number gamma between f of a and f of b, okay, let's see f of a and f of b. So f of a, so why is this claim true? Well, f of 0 equals 0 cubed plus 0 minus 1, and that's negative 1. And f of 1 equals 1 cubed plus 1 minus 1, and that's 1, right? Now, since 0 is between f of a and f of b, right, we have that gamma, so gammas are 0. What am I saying? 0 is our gamma. The intermediate value theorem says there exists at least one point in the interval from a to b such that f of c equals gamma. So the intermediate value theorem tells us I'll just call it IVT, tells us that there is a c in the open interval from a to b, c between 0 and 1, such that equals 0. Okay. By the way, when we say between, we should be clearer about what this means. So when we say the gamma is between f of a and f of b, we mean that, so i.e. gamma is bigger than f of a and less than f of b, or if f of b is less than f of a, then gamma is bigger than f of b and less than f of a. Okay. Because I was just thinking, what happens if f of a equals f of b? Then you could have something like, you could have like a parabola. Okay, I'll just draw a little cloud here. Right, if f of a equals f of b, then you can, you can have like a parabola like this. Right, so if you have something like this, and then the output's like 5, and this is your a and that's your b, then your f of a and f of b are 5, but there is no c in between a and b such that f of c is equal to 5, right? Even though this function is continuous. So what I mean is that f of a and f of b are not equal in this case. Okay. Now notice that the theorem only tells you that there exists at least one point. Doesn't tell you where, so I'll just put a little remark. The theorem doesn't tell you where. It doesn't tell you what C is. Exactly. Right? And there could be more than one C. Like in this example, there's more than one C. I mean, this example. Right? There's more than one C that will work. C could be this blue C, but C could also be here, and C could also be there. Right? Okay, and now one other remark I should make is that the continuity condition is essential because otherwise you can have A and B, and f of A, let's say it's here, and then f of B is, here, right? But you could have a gamma that's here, and then your function could be, it doesn't necessarily have to intersect this line. Like your graph could be well, it has to go through the 2 points, so there you go. That's an example of a function that goes through a comma f of a and b comma f of b, but it doesn't cross the line y equals gamma. Right. So the continuity is an essential part of the proof. If we just took the intermediate value theorem and then just like erase the word function, it would no longer be true. Okay. All right, let's look at a few more applications of this intermediate value theorem. So one interesting consequence is, Suppose that f is a continuous function from the closed interval from 0 to 1 to the closed interval from 0 to 1. Okay. Show that f has a fixed point, i.e. a point x naught in the closed interval from 0 to 1, such that f of x naught equals x naught. So it says that if you have a continuous function from 0 to 1 and the outputs are all in the interval from 0 to 1, then there must be some point x naught whose output is also x naught on the graph. So the graph has to pass through x0, x0 for some x0 between 0 and 1. All right, before I prove this, I think it would be a good challenge to pause the video and see if you can figure out why this is true before I reveal the answer. Okay, let's talk about the solution to this. So why is this true? The idea is there's a little trick. Consider the function. So we want to show, what we want to show is that f of x minus x, or f of x equals x for some, x in the interval from 0 to 1. In other words, i.e., the equation f of x equals x has a solution in the interval from 0 to 1. Well, there's a trick that will allow us to use the intermediate value theorem, and that's just to subtract both sides. So consider the function g of x equals f of x minus x. Well, to show that f of x equals x is the same as showing that g of x equals 0. So we want to show that g of x has a root in the interval from 0 to 1. And now we see where the intermediate value theorem comes in. We calculate g of 0 equals f of 0 minus 0 is equal to f of 0. And we calculate that g of 1 is f of 1 minus 1. Now, f of 0 is greater than or equal to 0 because f has range in the interval from 0 to 1, and g of 1 is f of 1 minus 1, and that's less than or equal to 1 minus 1, which is 0. So what's going on is the graph of g, okay, g of 0, here's 0, here's 1. G of 0 is either equal to 0 or it's above the x-axis, and g of 1 is either equal to 0 or below the x-axis, right? Now notice that we're trying to show that there's an x naught in the closed interval from 0 to 1. So obviously if either g of 0 or g of 1 is 0, we're done, because we can just pick x naught to be 0 or 1 respectively. Otherwise, g of 0 is greater than 0 and g of 1 is less than 0. So g of 1 in this case will be, g of 0 will be somewhere here, g of 1 will be somewhere below, and then by the intermediate value theorem, there is some x naught in the open interval from 0 to 1 such that g of x naught equals equals 0. And in this case, f of x naught equals x naught. So that's the proof. Okay, let's look at another example. And this example is the proof that roots exist, basically. So let's show that if let's just say y0 is positive, then it has a square root. Then y naught has a positive square root. Alright. So we're considering the function f of x equals x squared, right? Well, this is continuous. So let's just draw a picture just to get an idea of what's going on. So you have y equals x squared, and you have y naught somewhere here. Well, we know that f of 0 equals 0. And we know, for instance, that if you plug in y naught, well, that's not true. I was going to say that if you plug in y naught, then y naught squared is bigger than y naught, but that's only true if y naught's bigger than 1. So if, okay, so let a equal 0 and let b be, well, let it be y naught if y naught's bigger than or equal to 1, and let b equal to 1 if y naught is less than 1. Well, if y naught's less than 1, then y naught squared is less than 1. So in either case, whatever b is, then y naught is between f of a and f of b. Right? Because f of a is equal to 0, and then we designed b so that y naught is always less than that. So we have this, so then by the IVT, intermediate value theorem, there is some x naught in the open interval from 0 to b such that f of x naught equals y naught, i.e. x naught squared equals y naught. So every positive real number has a positive square root. So finally, we know that it does make sense to refer to the square root of a positive number. Okay, so the intermediate value theorem is actually very useful. And more generally, and then I'll just leave this kind of as an exercise, any positive number has an mth real root. positive mth root. And the proof is similar to what we just did. You just have to figure out how to modify it. All right. So that's the intermediate value theorem. And a reference for this, well, the intermediate value theorem is basically stated in any calculus textbook. But for the stuff that we were talking about later, and if you want to see a proof, you could see there's this book by Kenneth Ross, Elementary Analysis, the Theory of Calculus, for a proof of the intermediate value theorem. So, if you want to see a proof. That's a reference. And I'll probably make another video where I present the proof. Okay, thanks.